Today we will do a problem based on the Fourier series representation of wave equation. The question is, a string is stretched and fastened at 2 points L apart. Motion is started by displacing the string in the form y equal to k sine pi x by L, from which it is released at t equal to 0. Show that the displacement y of xt is equal to k sine pi x by L into cos pi at by L. So here the length of the string is given as L, and motion is started by displacing the string in the form of y equal to k sine pi x by L. Means the initial displacement is k sine pi x by L. That is the notation we are using f of x. F of x is k sine pi x by L. Also given that it is released at t equal to 0. That means the string is released from rest. That means the initial velocity is 0. That is g of x is equal to dou y by dou t at time t equal to 0 is 0. So our f of x is k sine pi x by L and g of x is 0, and we have to find the displacement function as y of xt is equal to k sine pi x by L into cos pi at by L. The wave equation is given by dou square y by dou t square is equal to a square into dou square y by dou x square. And we know that the solution of equation 1 is y of xt is equal to a cos lambda x plus b sin lambda x into c cos a lambda t plus d sin a lambda t. Let it be our equation number 2. Now we have to write the initial conditions and boundary conditions. The boundary conditions we know, it is y of 0t is equal to 0 and y of lt is equal to 0. That is, at the starting point and ending point of the string, the displacement is 0. Now the initial conditions, as we have seen, it is f of x is equal to y of x comma 0. That is, when time equal to 0, the initial displacement is f of x equal to, it is k sine pi x by L. As the string is released from rest, we have gx is equal to dou y by dou t at time t equal to 0, it is 0. So we have the boundary condition y of 0t equal to 0, y of lt equal to 0. The initial conditions are given, that is fx is equal to y of x comma 0 is k sine pi x by L, and the initial velocity g of x is 0. Now put the first boundary condition in 2. Applying the boundary condition a in 2. The boundary condition says that y of 0t is equal to 0. So you have to put x is equal to 0 and t equal to t as such. So we get 0 is equal to a cos 0, that is a, b sin 0, it is 0, into c cos a lambda t plus d sin a lambda t. This is by putting a in equation 2. This implies either a equal to 0 or this part is 0. But c cos a lambda t plus d sin a lambda t cannot be 0, because if it is 0, equation 2 becomes yxt is equal to 0. That is, the solution of wave equation will become 0. It is not possible. So we take as a equal to 0. So when a equal to 0, equation 2 reduces to, therefore equation 2 implies y of x of t is equal to b sin lambda x into c cos a lambda t plus d sin a lambda t. That is your equation number 3. In 3, we apply the second boundary condition b in 3. We apply the second boundary condition B in 3. The second boundary condition says that when x is equal to L, y of LT is 0. So you have to put x is equal to L in equation 3 so that y of xt is 0. Then we have 0 is equal to B sin lambda L. Instead of x you have to put L into C cos A lambda t plus D sin A lambda t. So we have a B equal to 0 or sin lambda L equal to 0 or this part is 0. Already we have seen that C cos A lambda t plus D sin A lambda t cannot be 0. So if B is also 0, if B is 0, equation 3 will become y of xt is equal to 0. That is also not possible. So the only possibility is sin lambda L is equal to 0. Sin lambda L is equal to 0 implies lambda L is equal to n pi. Sin theta equal to 0 when theta is equal to n pi. So sin lambda L equal to 0 implies lambda L is equal to n pi or our lambda is equal to n pi by L. So when you substitute the first boundary condition, you have the constant A equal to 0 and for the second boundary condition we get lambda is equal to n pi by L. So far we have y of xt is equal to B sin lambda x into C cos A lambda t plus D sin A lambda t. That is our equation number 3 where lambda is equal to n pi by L. Now we are going to apply the initial conditions D, that is g of x is equal to 0 or dou y by dou t at t equal to 0 in equation 3. For that first we will find dou y by dou t. So you have to differentiate equation 3 with respect to t. So that B sin lambda x is a constant and the derivative of C cos A lambda t is minus C A lambda sin A lambda t plus derivative of D sin A lambda t is D A lambda cos A lambda t. Now we will apply D in the equation 4. D in 4 implies D in 4 means dou y by dou t at t equal to 0 is 0. Therefore 0 is equal to, you have to put t equal to 0. So we have B sin lambda x into sin 0 is 0. So this part is 0. Cos 0 is 1. So that we have dA lambda. So when t equal to 0, dou y by dou t is equal to 0. That is our initial condition 4. So that we have 0 equal to B sin lambda x into dA lambda. Here B cannot be 0. Equation 3 will become 0. Sin lambda x cannot be 0. So that equation 3 will become 0. Then A and lambda it cannot be 0. A is the constant in wave equation and lambda it cannot be 0. Therefore the only possibility is this D can be 0. This implies D equal to 0. So the only possibility in this equation is D equal to 0 and that we substitute in equation number 3. So that our displacement function yxt is equal to B sin lambda x into, this part is 0, so that C cos A lambda t, or we can write BC sin lambda x into cos A lambda t. BC we will represent by AN because we are finding the Fourier series solution of the wave equation, and sin lambda x into cos A lambda t where lambda is n pi by L. So we have y of xt is equal to sigma n equal to 1 to infinity an sin lambda x into cos A lambda t, where the formula to find an is 2 by L into integral 0 to L f of x sin lambda x dx. Here f of x is given as k sin pi x by L. K sin pi x by L. So if your function f of x and g of x are sine or cosine functions, instead of doing the integration, you can use the method of comparison of coefficients. That will be more easier. So your f of x or g of x are functions of sin x and cos x. We can use method of comparison of coefficients. For that, we are going to apply the initial condition C in phi. So the initial condition C is y of x of 0 is equal to f of x. Y of x of 0 is equal to f of x, and it is given as k sin pi x by L. So we are going to put t equal to 0. Therefore, phi implies y of x of 0 is equal to sigma n equal to 1 to infinity an sin lambda is n pi by L x into cos 0 is 1. We are putting t equal to 0, so that cos 0 is 1, which implies y of x0, that is the initial displacement, is k sin pi x by L. F of x is k sin pi x by L. Now we put n equal to 1, so that a1 sin pi x by L, put n equal to 2, a2 sin 2 pi x by L plus n is equal to 3, a3 sin 3 pi x by L, and so on. So we can compare the coefficients. Sin pi x by L, the coefficient is k is equal to a1, or a1 is equal to k, and a2 is equal to a3 is equal to etc. is 0. All other coefficients are 0, and we are getting a1 is equal to k. So that we can substitute this in our equation 5, that is the final solution of the wave equation, the displacement function y of xt. So for n is equal to 1, we have y of xt is equal to a1 sin pi x by L cos a pi t by L, where a1 is k and the solution is k sin pi x by L into cos a pi t by L. That is the required displacement function.